Okay, so we're working our way through exam 1. We're on page 4, and we're looking at the mechanisms. So let's take a look at the top one here. Alright, we've got an epoxide, we've got an alkene, and we're asked to get from one side to the other, right? So we're just asked to, propose a mechanism to get to our product that's shown. But look, right, we've got an epoxide under acidic conditions. This is not the first time we've seen this on this exam even. So we will launch right into it. All right, so we're going to do protonation of our epoxide. Let me change colors here, sorry. Alright, so we're going to start out by protonating our epoxide here. There's that. Bond in purple to a blue hydrogen. Great. Okay. Now I'd ask you to go back and look at the previous video that we did where we talked about the, how an epoxide opens under acidic conditions, right? That oxygen is going to be pulling from one side to the other, right? Pulling from one side to the other, right? Leaving behind a partial positive charge on either the red or the yellow carbon. And it just so happens, right, that it's going to pull and leave a partial positive on that red, which lets our pi bond swing in and help pop that open, right? So I'm going to zoom in here for just a second. Right, and I'm going to let's number my carbons. So let's go 1, 2, 3, 4, 5. Okay, so I like to number my carbons that are involved with the mechanism here. Like I kind of start at what gets attacked. I usually give that the number 1, and then I kind of number my way back to where the electrons come from. Kind of just makes it a little bit easier. So this is telling me. Right? This is telling me that I make a 5-membered ring, right? This is telling me that I make a 5-membered ring. Because my 5 carbon is going to attack my 1 carbon there. So let's draw a 5-membered ring. Alright, let's start to put some colors on things here. We'll put that one in red there. That sounds good. Right, and let's number across. So that's number 1, 2, 3, 4, 5, right? So 5 attacked 1. Let's start to fill in what else was left over, right? If we look on our number 4, there was a methyl group there, and we notice that we left behind a positive charge, right? We swung open the pi bond there between 4 and 5 to leave behind a positive charge on the number 4 carbon there, right? Okay, so what else did we have? Well, number 1, right, was attached to my alcohol. Whoops, that's the wrong size. There it is. So we had that, and then we also, right, let's label this, right, and there's our yellow carbon right there, okay? Fantastic. So if you want to pause here and just take a look at what happened, right, this is kind of the tricky part of this mechanism, just kind of seeing what attacks what, okay? But my trick, number your carbons, go back and count to make sure you have the total there, and then you'll be good to go. Okay, now that we're at this point, let's bring in a nucleophile to help take care of that carbocation there. We'll bring in some water. Water will attack our positive charge. Sorry, I forgot about the colors here. Purple to blue. And there is our methyl group that came out. Right now we have water bound right here. There's our positive charge. Okay. And then the last thing that's going to happen is some more water is going to come and clean things up. Maybe it's water, right? It doesn't have to be water that comes and cleans things up, right? This right here, right? That could have been another epoxide ring, could have come and done it, right? But water is probably in a higher concentration here than than our material, but so just for an example, we do this, okay? And then if we follow this along, we will get to our product, right? We will end up at our product there. Fantastic. Let me zoom out. Not too bad, right? This isn't the first time we've seen this mechanism either. Right? This was one of our quiz questions, but there we go. Okay? Wonderful. All right, now we got something that looks a little bit more different, right? So we start out with a vicinal diol under sulfuric acid, and we add some heat to it, and we end up with this weird bicyclic compound here, right? All right, well, let's see if we can figure out what's going on here. Now, here we have an acid, right? If we have an acid, right, remember my kind of rules of thumb. If we have an acid, it's going to be usually used in the first step of the mechanism. And if you have an acid, make it act like an acid, right? And an acid's job is to get rid of protons, right, to give up its protons. So the first thing we're going to do is protonate an alcohol. Now that is not too unusual, right? That's kind of the theme of our chapter that we looked at is, right, what happens to alcohols under, acidic conditions, right? And what we figured out here, right, or what we figured out, I should say, is that, they are able to pick up a proton from acidic media, right? Oops, there it is, right? Great. So again, the question is, what are the consequences of our actions? What have we done here? Well, there's our buddy water, right? A good leaving group. So guess what good leaving groups do? Leave, right? So let's make that leave. Right, there's that. And so what did we leave behind? Well, if a leaving group leaves, right, we're going to leave behind a positive charge, a carbocation. Right, so let me mark this in red, right? Right, so that carbon there in red, it's a tertiary carbon, not a bad, right, not a bad place to leave behind a positive charge. But if you look next door, right, if we look next door, there we see a carbon that's attached to an oxygen. Right? Now, right now, that's a saturated carbon, right? We can't put any more bonds to it. But if we move one of the bonds, we can shift our positive charge. So what I'm going to do is take this bond here and send it over there, right? So let's see what happens here. We'll call this carbon number 1 in red, 2, 3, 4, 5, right? And let's number the yellow carbon there in 6. Let's number that yellow carbon there in 6. Okay? So we break the bond between 5 and 6 and make a new bond between 5 and 1. So what does this step look like? Well, we leave this side alone. Right? Our oxygen is still there. There's our red carbon. There's our yellow. Right? Okay. Right, that was carbon number 1, which is bound to number 2, which is bound to number 3, to 4, to 5. Right? So consequences of our action is we now have our positive charge there in our yellow. Right? We took a bond away from carbon number 6 there, the one dotted with a yellow there. Right? We took electrons away from that. Right? We broke a bond. Fantastic. Now what can we do? Well, now we have a positive charge that's next door. I'm just going to erase this here, just for clarity's sake. Now we have a positive charge on the same carbon that's bound to an atom that has lone pairs. Right, so let's plop down a pi bond. I'm going to draw this a little bit differently here, just to kind of clean things up. Oh, goodness. Okay. There's my oxygen. That's still bound to my hydrogen. And there's my double bond that I dropped down there, right? We'll put some color still. There's red. There's yellow, right? that carbon right there, I should say, right in that carbon. Okay. Now hopefully you can see what happens next. We have our double bond like we wanted. We just have to get rid of that black hydrogen there on the oxygen. So something's going to come and pluck it away. We could use water. We could use another alcohol. We could use the conjugate base of sulfuric acid, like whatever it might be. I'm just going to abbreviate it with a B minus, some kind of basic compound, right? Water and alcohol, whatever it might be. This would be just fine in this case. All right. And that will get us to our product there, right? And let me label our product just so we can track along. Right, there's that. All right, and then technically we had made one of these bonds in green there, okay? Fantastic. All right, this is also an example of a pinnacle rearrangement. So if you want to look that up, pinnacle, like P-I-N-N-A-C-O-L, right? So pinnacle rearrangement. Kind of an odd mechanism, right? We end up shifting a fairly stable carbocation, right? A tertiary carbocation to technically a secondary carbon there, but we can make a resonance stabilized carbocation, which is a favorable thing to do. Fantastic. Nice. All right, that's page 4. As a brief note, I'm going to look at page 5 here. Now, page 5 is, these were just synthetic routes, right? I was asking you to make these products in the highest yield possible. I am not going to cover this in the video. The reason why is just because there are a bunch of different ways that you guys could have accomplished this. I'm not going to cover this in the video because I have one way of doing it. There are tons of different ways of getting to all these different products. So what I want you to do is, here's the mechanism. Come see me, right? Come see me. Think about these. Look at what you did, right? Send me an email, snap me a photo of what you think might be the answers, whatever it might be. But come see me about these. There's a billion different ways to do it. I want you guys to figure out your own way, right? I want you guys to use your creativity and your strengths and your thoughts to come up with a synthetic route for this. Okay. Now there are better ways and there's worse ways of doing it. But remember, on paper, chemistry always works, right? The chemistry always works on paper, but there's always ways we can refine it. Okay. So come see me if you guys have questions about this stuff here. All right, and that's the end of the videos for exam 1 for Organic 2 in the spring 2019 semester.